Good afternoon, everyone, and thank you for joining us for this 7th webinar in the Offshore Wind Series, Learning from the Experts. I am Jana Herndon, Project Manager with NYSERDA's Offshore Wind team, and it's my pleasure to be joined by today's experts, Gordon Perkins and Kiva VanDerGeest with Environmental Design and Research, who will be giving a presentation on the science of visibility. Before I introduce our speakers, a few reminders for participants and some background on this webinar series. Next slide, please. Let's try that again. Next slide, please. Looks like I might be experiencing a delay on my end, but I will keep going. So if you are experiencing any technical issues, please contact Sal Graven. His email address will be on, there it is, on the meeting procedures slide. This webinar is being recorded, and the recordings and presentation slides for all webinars in this series will be available on NYSERDA's website at the address on this screen. All participants have been muted. We will have time for Q&A following the presentation, so please use the Q&A function to submit your questions for the speakers. Next slide, please. New York State is working to advance the responsible and cost-effective development of at least 9,000 megawatts of offshore wind by 2035. Offshore wind is a critical component in achieving the state's goals of 70% renewable sources of electricity by 2030 and 100% zero emissions electricity by 2040. While offshore wind has been providing clean energy to other parts of the world for several decades, this industry is brand new to New Yorkers. To provide interested stakeholders and members of the public with accessible, impartial information and opportunities for engagement on specific topics of interest, NYSERDA is hosting this educational webinar series called Learning from the Experts to connect the public with independent experts in key topics in offshore wind. We endeavor to select Learning from the Experts speakers based on their expertise and not necessarily for an alignment of opinions with NYSERDA or the state of New York. If you would like to suggest a topic or a speaker for a future webinar, please email us at offshorewind@nyserda.ny.gov. Please note that the views and opinions expressed in this presentation are those of the presenter. Next slide, please. It is now my pleasure to introduce Gordon Perkins and Kiva VanDerGeest. Gordon is a division manager at Environmental Design and Research with 20 years of professional experience. He is one of the leading expert consultants in visualization and visual impact assessment in the Northeast and has managed and/or served as lead technical specialist on visual impact assessments for multiple offshore wind projects reviewed by BOAM, as well as for onshore wind, solar, and transmission facilities reviewed under applicable federal and state permitting laws and regulations. Kiva is a visualization project manager with over 6 years of professional experience in planning, design, geographic information systems, and visual impact assessments. She has assisted in the development of visual impact assessments for energy projects, including onshore and offshore wind, solar, highway, and transmission facilities. Thank you for joining us today, and I will now hand things over to Gordon and Kiva.
Thank you, Jana. Sorry, slight technical difficulty there. Thank you to NYSERDA for inviting us to speak in this series, Learning from the Experts. And to everyone who's participating today, I hope that you find this information useful moving forward. As Jana mentioned, EDR has a long history in visual impact assessment. We as a company have been doing it for over 30 years. And my experience starts with the first offshore wind proposal in the United States, which was the Cape Wind project. We completed a visual impact assessment for that one. And then we also worked on the first offshore renewable energy project built in the United States, the Block Island Wind Farm. And our company and the Kiva and I have worked on roughly 2/3 of all current offshore wind proposals in the United States that are currently going through the permitting process.
I come to this field by way of planning. I'm a certified planner, and I was previously working at the municipal level with seeker projects going through planning board and GML 239 reviews, which, although very different, is also sort of shepherding these projects through substantial review at the environmental level. Currently, I'm working on a number of offshore projects between the Massachusetts, Rhode Island, Maryland, and New Jersey, these areas. And I've been working in permitting activities as well as administration of the VIA reports, field studies, and associated analysis. Just to give a brief agenda of what we're going to review today, I also want to point out in giving this that, we're talking about the science of visibility today, but that all leads into this report that's part of the permitting process. And so our agenda is outlined to go through the science of it, but it also sort of goes through the process that we use to develop the VIAs and the visual analysis that goes into the permitting process. So the first thing we start to do is develop the visibility thresholds. And these are really based on general facts about how far people can see, when visibility matters, and the difference between seeing something and being able to identify that thing that you're seeing on a distant horizon. We then use that information to establish a visual study area. And the visual study area is a regulatory extent of impacts roughly agreed upon by agencies and stakeholders. And this area begins to establish where impacts may actually be meaningful. With that, we determine the project visibility using a number of computer-aided processes, including GIS analysis and LiDAR data, to develop what we call an area of potential effect or a zone of visual influence, depending on what terminology. And we'll get into some of those terms later on in the presentation. We also back all that up with extensive field review. From that, we identify sensitive viewing areas from which we will create simulations. And then the development of visual simulations is a means to illustrate the project, the visibility of the project, and the potential for impacts. After that, determining the factors that influence visibility sort of brings everything full circle, and we take a little closer look at some of the variables that change visibility and the visual prominence of the scene that's being viewed. And then after that, if we have a little bit of time remaining, we want to make sure there's enough for questions, but we hopefully have enough time to touch a little bit on the recent regulatory agency guidance that was released from BOAM. So to start things off today, we begin with the development of visibility thresholds. So what factors contribute to the visibility threshold? And we've sort of divided these into the idea that some things are constant and some things are going to change. So the constants are going to be things like the curvature of the earth. That's what it is, and it's not going to change. Similarly, human visual acuity, although it changes from individual to individual, there's a range within which we know people are able to generally view the landscape. We know the size of the viewed objects. We know what height the view or elevation is going to be at. And we know the distance of the viewed object. However, the variables, the things that begin to change, are refraction. And when we're talking about that, we're really looking at how light is going to be coming through the atmosphere. And a good example of this is when you're viewing a distant island offshore. It can have that sort of floating effect where it's a little hazy at the bottom. And that comes from the refraction of the light. We're looking at atmospheric perspective. And this is how an object is affected by the space and atmosphere between it and the viewer. And this is going to be when distant objects become a little less clear. The colors begin to become muted and there's less vibrancy. We'll look at weather and atmospheric conditions. And obviously weather, a hazy day is going to be a different visual impact than a cloudy day. But we're also looking at the color of the sky and how the turbines sit in front of that. And then finally, the degree of available screening. And this is going to be trees or buildings and structures that could be in front of a viewed scene between the viewer and the wind turbines. And although something like a tree or a building, it seems relatively constant, it's not going to get up and walk away. The idea is that the viewer can. And in some of these analysis, a minor shift from the left to the right, a few feet in either direction, really makes a big difference in what you can see and how you see it.
So to build on what Kiva mentioned first, the curvature of the Earth, this is actually one of the easiest and best metrics for determining the visual threshold. And as you can see here, we've got a turbine that is extending away from the viewer, and the curve of the Earth is causing that turbine to appear behind the visible horizon. And this usually starts to take effect roughly around, if you're standing at sea level, it can start roughly around 15 miles, where a major component of the turbine starts to fall behind the horizon, and that would be the turbine platform. And then roughly around 20 miles, and again, this is dependent on wind turbine technology, but right around 20 miles, we're approaching the lower third of the turbine tower is obscured. 25 miles, the mid tower, and then 30 miles, we start to see screening of the nacelle, which is one of the largest components of the turbine and houses the generator of the turbine. And then beyond that, it results in blade tips only becoming the only visible component due to curvature of the Earth. And this is very meaningful because the blades are typically one of the smaller major components of offshore wind turbines, and they can be very, very difficult to decipher beyond a distance of 30 miles. So at sea level, curvature of the Earth becomes a significant factor at roughly 20 miles. And then viewer elevation is obviously going to change the way that profile looks. And as you can see in these two examples, we've got a sea level view on top, and then a highly elevated view on the bottom. And these are actual examples of the Block Island Wind Farm visibility, one from Cuttyhunk, Massachusetts, which has a very prominent lookout point, and the other one is from the mainland in Rhode Island. And as you can see, this elevated view really sees a lot more of the turbine when compared to similar distances when you're viewing from sea level. This is that same location on Cuttyhunk Island, looking out toward the Block Island Wind Farm. Obviously, we've got a standard view, a 50mm view in the upper left-hand corner, and that small box indicates the position of the Block Island Wind Farm from this location. And it's important to note this is roughly 33.5 miles away. And during my time doing this photography on Cuttyhunk Island, several residents, I think they have roughly about 12 to 15 year-round residents, and they came up to figure out exactly what it was I was doing up there. And when I pointed out the fact that I was looking at the wind farm, they simply could not see it with the naked eye, and could only view it under the aid of a 500mm lens. And we're going to dig back into this view from Cuttyhunk in a little bit, because that's not always the case. But in developing these visibility thresholds, we do account for curvature of the Earth, and we also account for the variable factor of refraction, which is the bending of light rays and can actually allow us to see beyond what the physical limitations of the Earth suggest we can see. And so in this study that we did in Cuttyhunk, we were developing a sort of standard threshold for visibility utilizing a refraction index, and we include that index in all of our models when completing visibility assessments and simulations. So going back to offshore wind visibility, obviously offshore wind turbines are very large. Current technology for projects that are being permitted can exceed 875 feet above the water surface. And future technology, as defined by the National Renewable Energy Laboratory, they have a model of a 20 megawatt turbine that is currently exceeding 1,000 feet above the water surface. The ocean and coastal landscape typically allow for panoramic long distance views. This is very different for land-based wind projects where you have a lot more screening elements in the midground and background, and of course the foreground. In an ocean environment, typically only those foreground screening elements come into play. Historic properties within a coastal setting are often considered sensitive to changes in the seascape. Obviously, you know, the United States has a long history of coastal development, and it goes back, you know, to the, you know, beyond European settlement. And these are very important places to us. And so we try to identify the range of types of sensitive resources within the coastal landscape. And then planned wind energy areas range from 10 to 40 miles offshore. All of this information leads to very large study areas and numerous sensitive receptors, which means a very, very large scale visual study as a result. One of the ways we start to narrow that down is to define a visual study area. And part of that is establishing what your visible extents are. And we do this through a geographic information systems analysis, GIS analysis, called viewshed analysis. And here we've got 3 examples of the different types of viewshed analysis. There's topography only. We've got topography and National Land Cover Dataset, which considers the screening effects of vegetation. And then topography, vegetation, and structures. Now, this last one is a much more accurate prediction of project visibility. It takes into account all of the screening elements available on shore and leads to a much more focused study. Topography only is useful in finding the visual threshold limit, and we're going to get into that in a little bit. But applying this to a project off the coast in the Mid-Atlantic region, we did a legacy or topography viewshed that suggested 28% of the study area would have visibility, and that's 317 square miles would require additional analysis, and we had 1,000 resources to look at. Once we add vegetation into this analysis, the screening by topography and forest vegetation results in 11%, so less than half of the study of the previous visible area is now showing as visible. And that reduced the number of resources that we have to look at down to 434. And then finally, we get into the LiDAR viewshed analysis, and that resulted in only 7% of the study area having visibility and 236 potentially historic resources within the zone of visual influence. Now, it's important to note here, just to back up a tiny bit, LiDAR data is a low-level flight recorded data that utilizes LiDAR and light to basically paint a picture, a very accurate picture of the Earth's surface. It can tell the difference between an asphalt surface and a grass surface, trees, buildings. And so the resulting product are just, for a study area like this, results in trillions of points that we then turn into a grid and use that to determine where project visibility might occur. Some of the drawbacks of this data, there can be, classification errors that result in major errors in the viewshed analysis. And this example, hopefully everyone can see my cursor, but there's a road sort of bisecting this image. And you can see on the side of the road, we have these white blips that occur along the side of the road or on the sidewalk. And these are actually road signs. And so we don't want those to act as screening elements. And so we actually go through the LiDAR and make sure that that information is not falsely suggesting that the project is screened. LiDAR has a huge requirement in terms of processor and memory. and the processing time requirements are huge to develop a visibility model. It's worth noting too that transmission lines, bridges, narrow hedgerows, and things like that are often interpreted as screening elements. And so we like to correct the LiDAR data to make sure that they don't falsely represent screens. And the reason for that is transmission lines are projected down to the surface of the earth and effectively make a curtain that would eliminate visibility. This is a verification of our viewshed analysis. We always do field review to make sure that our LiDAR analysis results are correct. And in this particular instance, the red dot is sitting on a position of visibility that suggests 3 to 4 turbines could potentially be visible at this location. And that's one of the nice things about viewshed is it does interpret magnitude of impact by telling you roughly how many turbines could be visible at an individual location. So when we went and verified this through the visual simulation process, which Kiva will get into in a bit, we did in fact determine that exactly 4 turbines were barely visible. Just their blade tips were visible amongst the buildings and trees in this particular location. So we have lots of verification techniques, and we like to make sure that we apply those because we do rely fairly heavily on viewshed results.
So once we establish our study area and we begin to develop the ZVI, or zone of visual influence, then we begin to look at what areas and specific places we believe to have potential visibility. And we call these areas key observation points. So what is a key observation point? So we begin by looking at what's already been identified as important. So things that have been identified by federal, state, local, or tribal official agencies are going to really give us a groundwork of the things that people already find to be important in their landscape. And these sorts of resources are typically things like National Registered Historic Places, or items listed on the National Registry of Historic Places, state parks, national parks, and state scenic areas. And then after that, we look for KOPs that provide clear and unobstructed views toward the project site. So roughly, is it visible and how visible is it? After that, does the KOP illustrate the most open views available from a variety of these sensitive resources or VSRs? And is it the worst case scenario? So we're looking for the most open views and oftentimes the closest views. The one caveat on the worst case scenario thing I would say is that we do want to represent what a typical view would be and what a typical viewer would experience, but in that we try to show something that is really highlighting the visibility of the project, so those open and closest views. Then we look at whether the KOP is representative of a larger group of candidate KOPs. It's impossible in a study area the size to simulate visibility from every location that could be impacted. So it's really important to look at KOPs that typify a variety of circumstances. So in those circumstances, obviously, we're looking for something that typifies a variety of the VSRs and geographic locations. But we'll also look at those that demonstrated typical views from a variety of landscape settings. So what does a beach scenario look like? What does a wetland scenario look like? Similarly, we look for typical views of the proposed project available to a variety of different users and different user groups, considering who's there and what their viewing experience could potentially be. And finally, we look for typical views from a variety of geographic locations that represent a variety of lighting conditions and illustrate a range of visual change that could occur. Because we want to show this worst case scenario, we want a variety in the way the wind turbines are viewed both in time and spatially. So this would get towards the idea of the changes in the sky color and whether or not the turbines could be backlit at sunrise in one location and frontlit at another location. Then we'd consider whether or not you see the full array of turbines from the east and what that view might look like, as opposed to what the turbine array may look like from the north. as well as the east, south, and west. So once we've determined those locations that we want to simulate, we begin to get into developing the simulations. And we need to accurately represent the existing conditions within these simulations. And so in order to do this, I'm actually going to skip around on this slide a little bit. We'll start down at the 50 millimeters. To accurately represent in a static image what people are able to see in the landscape, obviously is no small feat. So we really look at using the 50 millimeter. We find that to be the best lens to do this. It's the best, most natural recreation of a scene. And it sort of has that Goldilocks effect where it's not too wide and it's not too zoomed in. We really want the spatial scale relationships between the foreground and middle ground elements to be constant. If we use something that's more than 50 millimeters, it tends to overemphasize the project. And if we use something less than 50 millimeters, it tends to overemphasize the surrounding landscape. So in addition to the 50 millimeters really hitting that Goldilocks sweet spot of the lens world, it also does a lot when we reproduce these simulations. So the single frame simulations are easy to reproduce. It's easy to disseminate them to the variety of stakeholders. And the viewing instructions that go along with these simulations are relatively simple. So back up to the top of the slide, the simulations can be accurately represented as a variety of media formats. The 50 millimeter single frame and the 50 millimeter single frame can then be used to develop the 124 by 55 degree panorama simulations, the 50 millimeter video simulations, and a newer development is the 360 degree immersive video simulations. And the folks in the BIA world are all beginning to experiment with that because it is sort of a newer format technology. And in this, you know, we recognize that you can't recreate the human experience in a landscape. The smells, the memories, the focus in these scenes at an offshore location is not something that can be represented in a photograph, but we really know that the 55 millimeter, the 50 millimeter really fairly represents accurately what it looks like to be in that location. So we spend all this time making sure that our photographs of the existing condition fairly represent what you would see in the landscape. And so to make sure that the simulations themselves are as accurate as possible, we start to capture some of the survey data while we're out in the field capturing those photographs. And so it's really important in these simulations that they're spatially accurate and they represent the proposed project at the correct scale and in exactly the correct geographic location.
So to Kiva's point on survey, we've got an example of a KOP in Massachusetts on Martha's Vineyard. And survey is really such a critical component of these simulations because if you have a reference point that's set, say, 50 feet in front of the camera, and you have a survey error of 2 feet, that can result in as much as a half mile of deviation at a 10-mile offshore location. So as such, in a situation like that, the simulation could be compromised if the survey is not accurate. So when building these simulations, essentially we're creating a virtual camera that exactly matches the specifications and location of the physical camera that we brought out there to take the photograph. And we model the environment. You know, in this particular case, we've got a cone of view that looks out over all of these built elements. And in that, we can use LiDAR data, topographic data, and survey data in order to calibrate the position of the target of that camera exactly where it should be. And in that vein, when we place the project into that same geographic space, it's shown at the exact correct location, it's at the correct scale, and it's so important to make sure that all of these model inputs, including the construction of the project, are are placed in the scene correctly and accurately in order to make sure that we are representing the project fairly and accurately.
So one of the major factors that influences visibility offshore is the weather. So sort of circling back to those variable and constant factors of visibility, this is one of the huge variable ones. And while we don't necessarily include a lot of this component in our simulations because we're trying to show that worst case scenario, we do discuss likely weather scenarios in our report. And the information that we use for that comes from detailed studies drawing from years of airport meteorological and visibility data. And this is determining the frequency of potential visibility of offshore projects. Past studies have included 10 years of minute-by-minute meteorological visibility measurements taken from several airports near the study area for the offshore wind farm. These past studies suggest that in the Massachusetts, Rhode Island wind energy area, visibility to 20 nautical miles could occur during as little as 31% of the daylight hours in a given year. And that visibility out to a distance of 30 nautical miles may only occur during 9% of daylight hours in a given year. And it's important to note that this percent of visibility is spread throughout the year and the day. Hazy morning may become a clear afternoon. And this data also considers that sort of scenario throughout the year, the spring, summer, winter, and fall.
And I think to Kiva's point, understanding the frequency at which these visibility conditions occur based on past meteorological data, obviously we can't predict, when the project will be visible, but we can certainly make reasonable assumptions about how frequently it could be visible throughout the year. And, recent data, it's so important to note here that we're currently collecting our data from onshore sources, and this mostly occurs at airports. And so we're limited to the data that is produced at the nearest airport to the project site. This data is not the same as offshore data. In fact, recent studies suggest that visibility in the offshore environment could actually be 20% less. And this is specific to the mid-Atlantic region. It could be different elsewhere. It could be 20% less than visibility over land. And a perfect example of this is pictured below. This is on Montauk. I believe it's looking east, roughly around Ditch Plains Beach or somewhere like along that southern shore beach line. And in this particular instance, the weather report at the airport, which was MacArthur Airport, not that far away, suggested 10 miles plus visibility. And that's absolutely the case onshore. But when we went down to look out at the ocean, we'd be lucky if we could get 200 feet of visibility out over the water. And anyone living in this area that's listening right now knows this phenomenon. It happens so many mornings in Montauk where you just get this low bank that just hangs over the water and you've just got beautiful, sunny, clear conditions on shore. So a very important factor when using meteorological data, hopefully in the future, as more site assessments are completed, this data is being collected offshore. I'd love to see collaboration amongst developers to share some of this information to allow us to make better predictions in the offshore environment, so that we've got a good picture and years worth of data about how frequently visibility can actually occur offshore. So going back to Cuttyhunk again, as I mentioned, under certain conditions, it's very, very difficult to see these turbines. And, in talking to all of the residents on Cuttyhunk Island in Massachusetts, even on the clearest days, no one was even aware that the Block Island project was visible from the highest point on the island. And that visibility changes minute by minute, day by day. The turbines can suddenly become obscure. And then all of a sudden, after the sun has set behind the horizon, you think the day's over and no more light is appearing over the water. And then it suddenly struck the turbines, for a period of about 2 minutes. and the turbines very briefly appeared more prominent on the horizon. And I don't think that, you know, this visibility is anecdotal at best. We were doing studies on refraction when doing this, but it's still shocking how quickly the visibility can change when you're standing in a coastal environment. And then, of course, we have nighttime. Each one of the turbines is affixed with a aviation obstruction safety light, and as visibility can be loosely defined as reflected light that's being received by our eyes. When you have an actual light source, that visibility is extended fairly far and therefore can appear pretty prominently at night. Obviously, how we see those lights is influenced by competing light sources. So even ambient light resulting from the moon phase can change things pretty dramatically. And then weather, atmospheric conditions, and distance from the project all play into visibility of the lights at night. This is an example of how cloud cover influences visibility. A much closer view of the Block Island wind farm. This is from Newport, Rhode Island at the Brenton Point State Park, which is also a historic district and scenic area. And the Block Island wind farm is roughly 23 miles away from this location. In, you know, just gathering anecdotal evidence about visibility, I asked several tourists what they thought of the project, you know, if they could see it. And over 90% of the people that I spoke to were unaware that the project existed, and when told where to look, a portion of those couldn't see the project. Now, obviously, that could change under variable conditions, but even on a seemingly clear day, when you've got cloud cover that goes all the way down to the horizon, the turbines can become very difficult to see. And part of the reason for that is their contrast is reduced as a result of not receiving direct light from the sun, and no hard shadows are being cast. And this is a view of that project with a 500mm lens.
So once we've done all of this work, we've found our areas of visibility, we've simulated them, what do we do with it? So this gets into the visibility and visual impact report that goes with some of the permitting. And so while the presentation is focused on visibility influences, another major component of the visual studies includes the visual impact assessment. Visual impacts are quantified by assembling a rating panel and a rating system to determine the scenic quality of the existing landscape or seascape. Then consider the scenic quality of the landscape or seascape with the project in place. The delta, or the variance between these ratings, quantifies the potential visual impacts. And we want to note visibility is not the same as visual impact. As Gordon showed in a number of his slides, you may be able to see the turbines or portions of the turbines, such as blade tips, but does that impact view or the landscape that it's set in? So to sort of summarize all of this, what we've really been trying to illustrate here is the methodology of the visual impact analysis in a way that shows how viewing, which is oftentimes considered subjective, can be analyzed in a very scientific and reproducible way. So to review some of these things that we've looked at, the visibility thresholds and study areas should be established for each project individually, considering the components of each individual project. The LiDAR viewshed analysis is currently the most accurate means of determining visibility and can be used to measure magnitude with the limitations. Simulation should be accurate and representative. Simulations should be viewed according to specified viewing instructions. Simulations do not replace the human experience, but they are the best means of illustrating visibility and visual impact. Impact determination should consider the worst case visibility conditions, but it's also important to illustrate the most likely conditions based on the meteorological data and visitation patterns of those using the space. It is not possible to predict atmospheric perspective, but assessment of past meteorological conditions can provide a means to quantify frequency of visibility. Since we do still have a few moments, I do want to run through quickly some of the more recent guidance coming from BOAM. There's a few items that, although are very similar to what we have been doing in the past, there are slight shifts. So projects occurring within 23 nautical miles of shore, the study area should now be defined using digital terrain model, which is the first slide of the viewshed analysis that Gordon showed. And that's just to establish the study area. So it's going to look at the highest point on the turbine and the screening effects of topography and the curvature of the earth, and the study area radius, even within that, is not going to exceed 46 statute miles. Separate seascape, landscape impact assessment and visual impact assessment is to be submitted to BOAM. The seascape, landscape impact assessment looks at effects on the character of a place itself, and the visual impact assessment evaluates the project potential visual impact on the people who are using that space. BOAM guidance requires that both assessments evaluate the susceptibility to change and value attached to the view in order to establish a sensitivity rating. With the project in place, raters will then review the size, scale, geographic extent, and duration of the impacts to arrive at a magnitude rating. This magnitude rating results in an overall impact level that's defined as either major, moderate, minor, or negligible.
It's worth mentioning at this point the BOAM guidance for assessing the seascape and landscape, as well as the visual impacts, was recently released. And if people are interested in seeing that document, I think we can post that after the presentation has been completed. But at this point, I know we didn't dig into visual impacts all that much, or visual impact assessment. This was meant to be the science of visibility. But we'll turn it back over to NYSERDA, and we can field any questions that people may have.
Great. Thank you so much, Gordon and Kiva, for that really great presentation. We certainly appreciate all of the information that you covered, and we do have some questions coming into the Q&A function, but a reminder to our attendees to please submit your questions for the speakers through the Q&A function in the WebEx. So to start with, could you please explain if there are ways to mitigate visual impacts from offshore wind?
Yeah, I think generally speaking, there are a number of mitigation options available. Obviously, traditional mitigation measures are very difficult to employ, where, there are so many viewing areas that, for example, vegetative mitigation won't work for offshore wind. But certainly, fewer larger turbines is a way of mitigating impacts. They tend to take up slightly less space on the horizon, and they reduce the phenomenon called stacking, which is when you're looking directly down a row of turbines from shore, and it can create this sort of discordant mix of objects and turbines at different rotation angles that can be a little bit disconcerting. So certainly fewer larger is great. And then for nighttime, there's an amazing technology called Automatic Detection Lighting System, or ADLS for short. And essentially what that does is it defines an airspace around the project, and every time an aircraft enters that airspace, they're given ample time to detect the wind farm because it will activate the lights. And the rest of the time, when there are no aircraft within the airspace, the lights are completely off. And that all but eliminates the nighttime visual impacts associated with the aviation obstruction lights.
Great, thank you, Gordon. I have another question here. What considerations for visibility are needed for different types and sizes of wind turbines used offshore versus land-based versus potential freshwater lakes wind generation?
Yeah, and I think each one of those study areas has to be treated slightly differently. I mean, the takeaway is we have to establish a potential zone of visual influence. That's an important component to each one of these projects. But the extent of that zone is going to change dramatically dependent on the technology that you're using. In my experience, freshwater renewable energy projects tend to have smaller technology, and then as a result, we'll have a much smaller viewshed. And that's a very important consideration, especially if you're far enough offshore that curvature of the earth comes into play. And then, you know, generally speaking, I think that probably the biggest difference there is going to be the size of the technology. And that will, you know, in the offshore world, we're already talking about, you know, 12, 15, 20 megawatt turbines. There's more consistent and more predictable wind offshore that can drive those larger turbines. Not so much the case when we're talking about freshwater wind in the northeastern United States, and certainly not so much the case when you're talking about land-based projects, which are typically in the range of between 3 and 8 megawatts at this point. In fact, I don't think we've exceeded 5 megawatts for onshore projects. That's the primary change between those.
Thank you. A question here that refers back to the variability in weather conditions offshore. And as you mentioned, visibility on the coast or in the offshore environment can be quite different from what you're currently experiencing onshore. But given that variability and what you've noticed in your studies, is it possible to estimate, based on those weather conditions, approximately how frequently turbines will be visible at a certain distance? You know, is it possible to give a rough percentage from this viewpoint, turbines X miles away will be visible this percentage of time, or are weather conditions too variable to make that sort of determination?
So it's certainly not a predictive technology. You know, just because it was sunny on January 10th, 2011, obviously doesn't mean it's going to be sunny January 10th, 2022. However, the frequency is fairly easy to predict. And when doing these weather studies to determine visibility, first of all, we have to include an equation that projects visibility out beyond 10 miles. And that's a fairly simple thing to do using humidity and cloud cover and things like that in order to project those visibility models out to an offshore situation. And in doing that, you know, a lot of these airports have been collecting data for years and years. And if you can get, say, for example, a decade of weather data from multiple airports near the project, you've then got a database that's big enough to predict future conditions as it relates to frequency. And that's a really important distinction, but I still think it's an important fact. You know, if you're able to say that visibility to 30 miles only occurs in a very small percentage of the days throughout a year, that really changes how much impact that project can have. And so certainly having a system by which we can predict offshore visibility is beneficial to the visual study. Having actual offshore data would be fantastic, and I think it would paint a very much better picture for how those projects might appear under different conditions. But given the technology that we currently have, I think that you know, as long as you're looking at a very large data set and verifying variability from year to year, you can paint a very accurate picture of frequency in the future.
I think also, technology's changed a lot with say the visual simulation process over a very short amount of time. And given the historical relationship between airports and weather data, obviously that's the place that a lot of that data is coming out of. As far as viewing from a specific location at a specific site and looking at the weather data in time and space at that location, that's certainly something that technology could one day catch up with. And it's probably not that distant on the horizon. So it's something that, all of us are definitely keeping our eyes on, and I'm sure a lot of folks out there are as well.
Thank you. Speaking of on the horizon, another related question, harkening back to the curvature of the Earth. So on that slide where you had illustrated that a significant part of the turbine is hidden from view at around 20 miles away, what size turbine are you assuming there? And then part two of that question is, at that distance away, and given all of the data that you've looked at through various assessments, are you able to say about what percentage of time the turbines at that distance would be visible based on weather conditions, or is it too variable at different places along the East Coast? And we're talking specifically about the Northeast here.
Yeah, and I think, so as far as the curvature of the Earth model goes, the example that I showed, I believe was either a 6 or an 8 megawatt turbine, which had a maximum height of 678 feet. Obviously, as turbines get larger, the screening effect of the curvature of the Earth is reduced. However, it's not really that dramatic. By the time typically tower heights are going to max out at a certain point, and rotor diameters can get a little bit bigger. And so the point at which the nacelle typically becomes screened remains relatively constant across many of the different turbine types. Not the case for very much larger turbines such as a 20 megawatt, which we really haven't started studying yet. But the visibility of that type of unit would extend out further. One thing of note is that as you hit that 25-mile mark or 30-mile mark, it really starts to diminish very quickly. And so right around that 40 to 50-mile mark, I think that distance is going to vary. Most current technologies are going to get buried behind the horizon. And then again, the question about visibility conditions, certainly as long as the data exists at local airports, we're able to predict frequency with, I think, with fair confidence based on multiple years of previous data. I do think that as we collect offshore data associated with site assessments, it would be beneficial if there could be a central pool for that data so that consultants can draw from that and really make more realistic predictions offshore. Now, EDR's got a number of studies that we're dreaming about, as well as undertaking in order to try to capture some hard data that uses the AIS system which is predicts or notes the position of offshore vessels, and having that data live gives us the opportunity to actually photograph conditions when those ships or vessels are predicted to be in a particular location and distance offshore. And so it's actually, we're able to verify real-time data, and we do this when we go out and photograph KOPs. We use the AIS system to locate those vessels and determine their visibility, and we also use them, frankly, in the alignment process as well.
Thank you. Can you talk about how blade movement is considered in a visual impact assessment?
Certainly, yeah. And Kiva got into this a little bit when we talked about the visual simulations, but typically, and there's a little bit of difference of opinion about how blade movement attracts viewer attention. Certainly, within a distance of 25 miles, and you're in a dynamic environment where there are people running around, there's kites flying on the beach and things like that, the movement of wind turbines will draw viewer attention. There's no question about it, as long as those turbines are visible. When doing visual simulations, one thing to note on that is we're always focused directly on the project. And therefore, really drawing somebody's attention to that project is not necessary at that point because you're already looking straight at the project. However, in order to illustrate how that movement might change the visual characteristics of the project, we do create subsets of visual simulations that include motion. So you can see the waves, you can see people walking around, birds flying by, and the turbine spinning in the background. In addition to that, we're in the process of developing a system by which we can do 360-degree VR visual simulations. And one of the major limitations in this technology is it's not quite there resolution-wise. So a project that's located 30 miles offshore, the turbines would have to be shown at an immense resolution in that video. And they haven't quite gotten the video recording systems to that resolution yet. But for closer projects, we can actually give people a picture of what they look like in a completely immersive environment. So you can stand in a location, put goggles on, and do a complete 360-degree field of view. And in those cases, I think that turbine blade motion is certainly going to enter the equation. It will draw viewer attention. Especially
when they're stacking, as you mentioned before.
Yeah, exactly. Kiva just brought up the stacking thing again. So if you have turbines that are rotating at different speeds in different portions of the wind farm that are perfectly aligned in a row, you're going to kind of see blades sticking out at different angles, and that will draw viewer attention. In addition to that, it's worth mentioning that when the sun's very low in the sky, there is this phenomenon called glint, which can result in a very, very slight light reflection from the turbine. And on occasion, and this is pretty rare, but on occasion that glint can just catch a viewer's attention for a second. So certainly movement does play into this. And, for onshore projects, we've found that the viewing public generally sees these projects more favorably when they're operating. And I think this goes for anything. If turbines are static, they appear as derelict and non-functioning, and they're not contributing anything. So movement can do a couple of different things. It can draw attention, it can draw inspiration, and it can actually make turbines appear as though they are actually functioning and doing something good.
Thank you. And I think we have time for one more question. Can you talk about seasonality in terms of vegetation when creating your visual simulations? And relatedly, do you need to take pictures during a best case scenario, cloudless, perfect temperatures in order to create visual simulations?
So I'll take the first question. So seasonality is an important consideration in that when we look at the factors that affect visibility, generally those visibility due to atmospheric conditions can be higher during the fall and winter months and portions of the spring, although spring also brings weather systems that are can really mess up our field work and visibility. But anyway, The seasonality of leaf on, leaf off, I think has very minimal effect on in the offshore environment, particularly because we are not choosing KOPs that are hampered by vegetation in any way whatsoever. We're picking prominent open views. Now, certainly in some locations, you may have a view of the ocean during the winter time that you didn't have during the summertime. And in those situations, certain portions of the horizon could become visible. And that's important when projects are closer to shore, certainly. But for distant projects, even the leafless branches of trees can act as screening elements in the landscape. And so for that, I think, you know, the leaf off, leaf on conditions really doesn't change the course of the assessment or the KOPs that we choose.
To Gordon's point, trying to distinguish a blade turbine from a branch in between the view. So a very distant turbine blade tip above a leafless tree branch can be very difficult.
Yeah, we've tried to do it. And there was a second part to that question, Jenna. Do we have time to revisit that really quickly?
Quickly, the second part was, do you need to take pictures during perfect conditions in order to create visual simulations?
I mean, ideally, certainly that is helpful to have images that where you've got long distance visibility and the horizon extends out as far as it possibly can. We've collected enough field data now for enough projects on the East Coast that if these conditions simply don't present themselves when we're out in the field, and we try like the devil to get them, but if we're just unable to capture perfectly clear conditions, it is possible to digitally alter images in order to project that horizon out. And we do this through mathematical models. And, you know, we use these mathematical models to predict where the horizon would occur before simulating the project in the view. So ideally, yes, we would love to capture all of our images under perfect weather conditions. But as we mentioned in those meteorological studies, sometimes that occurs over the course of 9% of a given year. So it makes it very difficult.
Great, thank you. And thank you to our attendees for joining us for this Learning from the Experts webinar. I'll just close us out with our final slide. A reminder that the webinar recording and presentation slides will be available at nyserda.ny.gov/osw-webinar-series. Our next webinar in the series is on July 7th. Neil Weisenfeld and Garrett Moran with ICF will present on offshore wind resiliency planning. And on July 28th, Chris Oleth with the Special Initiative on Offshore Wind will present on offshore wind stakeholder engagement. You can register for these and future webinars through our events page at wind.ny.gov. If you have requests for future topics you'd like to hear about in this series, please email us at offshorewind@nyserda.ny.gov. Thank you again, Gordon and Kiva, and thank you all for joining us today. We'll see you next time.
Thanks, everybody.